Hi, my name is Bahadur Ahmedov. In this video lecture, we are going to discuss about how to find the Fibonacci numbers. So the Fibonacci numbers are given in the following sequence. So they start from the 0 and 1, and in order to find the next one, we need to always add the previous t. For example, if you add 0 and 1, you're going to get the 1. If you add 1 and 1, you're going to get the 2. And if you add like 1 and 2, you're going to get the 3, and so on. So for example, if you add the 5 and 8, the next term is going to be equal to 13. If you add the 8 and 13, the next term is going to be equal to the 21, and so on. So this is how it works. And what we want is now, I would like to figure out what's going to be the general formula for the Fibonacci sequence. So the general recursive formula for the Fibonacci sequence is that if you would like to find the k plus second Fibonacci number, you need to add the previous t, so fk plus 1 plus fk. That's a recursive formula. And if you would like to use this recursive formula, you need to find all the previous Fibonacci numbers. So our goal for this lecture would be to find the FK without finding the previous ones, without finding previous numbers. Well, we can do this using so-called diagonalization of a matrix. But before we do this, let's discuss where the Fibonacci numbers came from. So essentially, the Fibonacci is an Italian mathematician who wanted to understand how the population of his rabbits can increase. He used to have just a pair of rabbits, so they are newborn and they are not mature, so they're becoming mature in 2 months. And after they became mature, so they're going to give a birth to the newborn pair of rabbits every month. So essentially, in January, he used to have just a pair of rabbits. In February, so they are still not mature, so that's why they're not going to give newborn rabbits. In March now, so he has now the mature pair of rabbits. So they are going to give a birth after 2 months. So essentially, in March, he is going to have two pair of rabbits. So in April, he is still going to have these two pairs. Now, since his red pair of rabbits are mature, they are going to give a birth every month, while the blue one is not mature. So the blue one is not going to give a birth in April, but the red one is going to give a birth in April to the newborn rabbits. So in May, he still is going to have three pair of rabbits, but now there are two pair of rabbits which are mature. So essentially the red pair and the blue pair, and they are going to give a birth in May, while the black one is not. So essentially he's going to have five rabbits now. So if you go to one more month later, so he is still going to have five of this pair of rabbits. And in that case, three of the pairs are going to be mature. So essentially the black one, the red one, and the blue one. And they are going to give the new birth to the newborn rabbits. In June, he's going to have simply the eight pair of rabbits. Here is a simple model, and if you would just write down the number of the pair of rabbits, in January it used to be 1, then 2, then 3, then 5, then 8. You see, so these numbers are essentially the sum of the previous two. So that's where the Fibonacci sequences came from. And it is still used in biology as in order to understand the population of some animals. Well, what we want is we would like to look to this problem mathematical point of view. So we would like to try to understand how we can find the case Fibonacci number without finding the previous ones. Well, here we've got a recursive formula. So in order to find the case Fibonacci number, we would like to introduce the vector. So the UK vector is going to have two Fibonacci numbers, essentially fk plus 1 and fk. For example, if you would like to know what is the vector u0, you just need to substitute here and here, k to be equal to the 0. So that's going to be f1 and f0. So if you look to what is the values for the f1 and f0, so what are the first and zeroth Fibonacci numbers? They are simply 1 and 0. So essentially, this vector u0 is going to be equal to the 1 and 0. Well, 1 and 0. So the vector u1 is, in this case, is going to be f2 and f1. And if you look to this sequence, you see that this is going to be 1 and 1. So in general, uk is going to be equal to the fk plus 1 and fk. And if you substitute k was the k plus 1, for example, what's going to be uk plus 1? In this case, it's going to be fk plus 2 and fk plus 1. So I've got this by just substituting this k here to be equal to the k plus 1. So the reason why I wrote this, I would like to figure out the equation which will give me fk plus 1 from the, uk plus 1 from the uk by just multiplying uk to some matrix. So let's write down the recursive formula here. So the recursive formula is looking like this. At the same time, I can just simply add one more equation artificially. So this is essentially fk plus 1 is equal to fk plus 1. And I just added in order to create a system. So I've got the system of equations, and I can write this down as the equality of the two vectors. On the left-hand side, I've got this vector, which is going to be fk plus 2 and fk plus 1. And on the left, we've got another vector, fk plus 1 plus fk and fk plus 1. So we've got these two vectors which are equal, which will lead to the system. So essentially, we can write down this matrix here. So this vector can be written down as the multiplication of a matrix as a vector. So essentially, I can write this as a 1, 1, 1, 0 times to the fk plus 1 and fk. So you can see, you can quickly check that if you multiply this row to this column, you're going to essentially get this one. If you multiply this row to this column, you're going to get the second row of this matrix. So what we did is, so if you look carefully to this vector, this is nothing else as the uk plus 1. So this is uk plus 1. And if you look to this vector, this is nothing else as the uk. So this is uk. So you see, so if you multiply uk to some matrix A, was the following entries 1, 1, 1, 0, you are going to obtain uk plus 1. So essentially, we've got this matrix equation, and we're going to now use this in order to try to understand how we can find a uk. So let's do this. So uk plus 1 is equal to the a times the uk. For example, what's going to be u1? u1 is going to be a times the u0, which is equal to 1, 1, 1, 0 times the u0 is going to contain fk plus 1, so essentially f1 and f0, which is like a 1 and 0. Well, if you multiply this row to this column, you're going to get 1. And if you multiply this row to this column, you're going to get 1 again. So you see, so you've got the pair of numbers, so pair of Fibonacci numbers, 1 and 1. Well, if you multiply if you would like to find u2, for example, you're going to multiply a to the u1. So which is going to be 1, 1, 1, 0 times to the 1 and 1, which is going to be simply the sum of these two columns. And that sum is going to be 2 and 1. So essentially, here is this pair of Fibonacci numbers, 2 and 1. So if I would like to find a u3, then I can multiply the a to the u2. At the same time, I know that the u2 is equal to the a to the u1. So u2 is equal to the a to the u1. At the same time, I know that the u1 is equal to the a to the u0. So this is equal to the a times to the a times to the a to the u0. So essentially, u3 is equal to the a cubed times to the u0. Well, it gives me some hints about how we can find the uk, so essentially, which contains the Fibonacci number fk, without finding all of the previous ones. So we just need to know the first one only. So we've got this recursive formula that uk plus 1 is equal to the uk. So then that's why, so we can derive the equation that uk is equal to the a in the power of k times the u0. So we can continue this. We've just discussed it, that hey, u1 is equal to the a u0, u2 is equal to the AU1, and if you substitute u1, it's going to be a squared times the u0. u3 is equal to the AU2. If you substitute a u2 into here, so it's going to be a cubed times the u0, and so on. In general, you're going to get this equation that uk is going to be equal to the a in the power of k u0. Well, what the problem is, we are given this matrix A, and we need to find the k's power of this matrix A, and we are going to use the diagonalization of this matrix in order to find its k's power. Essentially, the A can be written as a multiplication of its eigenvector matrix to the eigenvalue matrix to the eigenvectors matrix and its inverse. So if you can write this down, this matrix A, as a multiplication of the three matrices, you can find A in the power of k, which is going to be equal to the x times the lambda in the power of k times the x inverse. So that's our goal, and that's our plan. So we would like to find the diagonalization of this matrix A. Then we can find A in the power of k by just powering up this matrix lambda. So in order to find the diagonalization of any matrix, we need to find its eigenvalues and eigenvectors. Well, let's find the eigenvalues of this matrix. If you remember, in order to find the eigenvalues of any matrix, we need to find the determinant of the A minus lambda I and equalize this to the 0. So the A is 1, 1, 1, 0. So minus lambda times the I is 1, 0, 0, 1. So which is going to be equal to the 1, 1, 1, 0 minus lambda 0, 0, lambda. So what we just need to subtract the lambda from the diagonal entries of this matrix, which is equal to the 1 minus lambda, 1, 1 minus lambda. So we need to find the determinant of this matrix and equalize this to the 0. So essentially, if you find the determinant of this matrix, it is going to be equal to this multiplied to this one, which is equal to the lambda squared minus 1 minus lambda, minus this multiplied to this, which is equal to the 1. So this is equal to the 0. And we can find the values for the lambda, which makes this equation to be equal to the 0. And those lambdas are nothing else as the roots of this quadratic equation. If you remember, in order to find the roots, we need to find a discriminant, which is equal to the 1 plus 4 times the 1 times the it's minus 1, so with this minus it becomes 1, so this is equal to the 5, and the lambda 1 is going to be equal to the 1 plus square root of 5 over 2, and lambda 2 is equal to the 1 minus square root of 5 over 2. So we found the two eigenvalues of this matrix, and now we need to find the eigenvectors. The problem is those eigenvalues here for this matrix are a little bit ugly. So instead of just using those values, I would like to use an abstract eigenvalue lambda. So in order to find the eigenvectors, we need to find a matrix first of all. So this matrix is going to be equal to the A minus lambda I, and we need to find its null space. If you find this matrix, it's going to be 1 minus lambda, 1, 1 minus lambda. And in order to find the null space of this matrix, we need to bring this into the row echelon form. So I would like to interchange the first row with the second. And if you do that, what you get is 1 minus lambda, 1 minus lambda, and 1. So we need to get rid of the 1 minus lambda. So in order to do this, I'm going to multiply the first row to the lambda minus 1 and add this to the second. What we get is essentially, it's going to be 1 minus lambda, so it's going to be 0 here, right? And minus lambda times to this one, it's going to be minus lambda times to the 1 minus lambda minus or plus 1 in this case, right? Okay, so if you look to this term really carefully, what you get is it's like a lambda minus lambda in the square plus 1, or minus lambda in the square plus lambda plus 1. So please know that the lambda is essentially lambda 1 and lambda 2. You just need to substitute lambda 1 and lambda 2 to there. And if you do that, this is equal to the 0 because lambda 1 and lambda 2 are the roots of this equation. I mean, we found the lambda 1 and lambda 2, which makes this equation to be equal to the 0, though. That's why it's going to be equal to the 0. So what we get is essentially it's going to be 1 minus lambda, 0, and 0. And could you please tell me which vector is going to make this this multiplication to be equal to the 0 and 0, since we need to find the null space of this matrix, right? And that vector is going to be simply lambda and 1. Because if you multiply this row to this column, you're going to get 0 and 0. Okay, so that's going to be the both of the eigenvectors. So essentially, the first eigenvector is going to be lambda 1 and 1. And the second eigenvector is going to be equal to the lambda 2 and 1. That's kind of easy, right? So we found the eigenvectors without using the values, actual values of the eigenvectors, symbolically. Well, now I'm going to put all of this eigenvalues. Yeah, so here is the eigenvalue problem, right? So if you multiply this and this, we are going to get 0 and 0. We've just discussed it. So that's why the eigenvalues are going to be lambda 1 and 1 and lambda 2 and 1. So we are going to put them together to one matrix, and this matrix is going to be called as the X matrix. So what we want is we would like to now find the inverse of the X matrix. And if you remember, there was a formula. So the inverse of the A, B, C, D is going to be equal to the 1 divided to the AD minus BC times to the DA minus B and minus C. So analogously, the inverse of this X is going to be equal to, so to the determinant of this matrix, which is like a lambda 1 minus lambda 2, times is that we need to interchange A and D, it's going to be 1 and lambda 1. And then we need to multiply B and C to the minus 1. So it's going to be minus lambda 2 and minus 1. So, well, that's going to be the inverse of the X. And if you combine all of these numbers together, all of these matrices together, so I've got 3 matrices. So X inverse in the lambda. Lambda is going to be lambda 1, 0, 0, lambda 2. So essentially, the multiplication of the X to the lambda and to the X inverse are going to give us exactly this matrix. So, well, if you remember, if you would like to find a UK, you need to multiply the A in the power of K to the U0. So the A in the power of K times the U0, so this is U0, is going to be, so this multiplication of the X to the lambda in the power of K to the X inverse, it's the A in the power of K, right? Times to the U0. This is what we get. So I would like to now, first of all, multiply these two vectors at the end. So what does it mean that the whole matrix is multiplied to this vector? It means that the first column is going to be multiplied as a 1, right? So the first column is going to be multiplied as a 1, and the second column is going to be multiplied as a 0. So that's why you're going to get simply 1 and minus 1. Well, if you don't remember what is the multiplication of the matrix as a linear combination of the columns, you can just simply multiply these matrices and a usual row by column matrix multiplication, and you're going to get the same answer. We are now going to multiply these two matrices. So if you remember, when you multiply a diagonal matrix from the right, so those entries on the diagonal are going to be multiplied to those corresponding columns. So the lambda 1 is going to be multiplied to the first column, and the lambda 2 is going to be multiplied to the second column. So please note that they are powered up to the k. So that's why this multiplication is going to be equal to the lambda 1 in the power of k plus 1. And lambda 1 in the power of k, because lambda 1 in the power of k is going to be multiplied to the first column. So the second column is going to be lambda 2 in the power of k plus 1 and lambda 2 in the power of k. So that's going to be the multiplication of the first two matrices. The multiplication of the last two matrices are going to be simply 1 and minus 1. And all of those things are going to be multiplied to the 1 over the determinant of this matrix, right? So please note that this multiplication is going to give you UK, right? So essentially AUK is equal to the A in the power of K times the U0. So this is what we want. And at the same time, UK by the definition was FK plus 1 and FK. So this is equal to all of this multiplication. So we just multiply these two matrices and we've got this matrix. And if you multiply this two, you're going to get this matrix. And if you multiply this one to this, it means just multiply the first column to the 1. So the first column is going to be multiplied to the 1. And the second column is going to be multiplied to the minus 1. So essentially, we just need to subtract the second column from the first one. So the FK plus 1 and FK is going to be equal to lambda 1 in the power of k plus 1 minus lambda 2 in the power of k plus 1, lambda 1 in the power of k minus lambda 2 in the power of k, times this determinant, 1 over determinant, it's going to be this number. So do you remember what we wanted? We wanted to find the fk, right? So we just need to equalize this. So the fk is equal to the second row of this vector multiplied to the 1 over determinant, or 1 over lambda 1 minus lambda 2. So this is what we get as the fk. So let me write this down now. So the fk is going to be equal to the second row, right? So if you remember, lambda 1 was equal to the 1 plus square root of 5 over 2, and lambda 2 is equal to the 1 minus square root of 5 over 2. And if you subtract them, what you get is simply square root of 5. And that's here. So square root of 5 is lambda 1 minus lambda 2. And lambda 1 is in the power of k is this number, lambda 2 in the power of k is this number. And if you evaluate this number here, lambda 2, and its absolute value is going to be a number which is smaller than 1, because this is a number which is slightly more than 2. And if you subtract the 1, it's going to be slightly more than 1. And if you just divide this to the 2, obviously this number is going to be equal, it's going to be less than 1. And this number, lambda 2, is going to be powered up to some k, right? And as k goes to the infinity, so for the large values of the k, lambda 2 is simply going to be equal to the 0. So we can basically neglect the second term, and we can write this down that the fk is going to be simply equal to 1 over square root of 5 times the 1 plus square root of 5 over 2. So in general, you just need to substitute the values for the k to here, evaluate this number, and take the nearest integer. For example, if you would like to find the 20th Fibonacci number, just substitute 20 instead of k. And if you do that, what you get is 1 divided to the square root of 5 times the 1 plus square root of 5 over 2 in the power of 20. So if you take a calculator and do those calculations, you're going to get the f20 is going to be equal to this number, 6,765.00002. And since we're making this approximation, do you remember why it's approximated? Because it used to be 1 minus square root of 5 over 2 in the power of k term as well. So since we're taking so we are just neglecting this term, then you are always going to get the nearest integer to this one, and the nearest integer to this one is equal to the 6,765, and that's going to be the 20th Fibonacci number. And you can check it up in the Google. So just type the 20th Fibonacci number, and you're going to get exactly this number. So in general, we can find the Fibonacci numbers using the recursive formula by finding all of the previous numbers, or also the previous two, or we can find a case Fibonacci number using this recursive formula, which has been obtained using the diagonalization of matrices. So thank you very much for your attention. I hope that this video was helpful for you.